Today's lesson is Chapter 3, Section 5, Mathematical Modeling and Variation. Please open up your textbooks to page 289. You'll definitely need it today for a couple of the story problems that we're going to take a look at together. So get on that page now and notebooks open and we'll get this started. There's a lot of different kinds of mathematical models. One of them that you guys are quite familiar with would be linear models. Scatter plots are generally one of the graphing forms that go along with these linear models. You guys know from past experiences with things like scatter plots that very often the data sort of kind of lines up. It doesn't make a perfect line, but it has what's called a correlation. When the dots kind of line up and do this kind of number. Remember seeing scatter plots that do that? It kind of mimics or looks sort of like what a positive slope or a positive line would look like. It's called a positive correlation. Some other times with your scatter plots, data might kind of do this instead. Okay, that would be called a negative correlation. Okay, but for either of them, we can find something that's called a line of best fit. That should ring a bell from the past as well. And it is a linear model. It's like a y equals mx plus b type of model. And we're going to talk about that for a little bit here first. Now there's a feature on your calculator that helps us come up with that line of best fit, more so than simply copying the scatter plot onto our paper, physically drawing a straight line centered through the data as best you can. It's called a least squares regression. Okay, so if you don't have a graphing calculator at home, make sure that we go through these steps together because you should get to punch them in and use that feature just like anybody else who happens to have the calculator at home. I would assume that those free downloadable graphing calculators would also have the ability to do this, and the keying in is probably similar to what we're going to go through here with the TI-84. But still, you're going to want to be able to do that on the calculator. So make sure that we go through that with you if you aren't able to do it now. All right, so on the calculator, find the linear regression feature. It is under the stat key. When you press stat, okay, there's a lot of options across and down. Choose edit. It's the top one on the list, and that's going to open up a table where you're going to be entering in ordered pairs. Now the table is going to say L1 for one column and L2 for another column. L1 is the X value of the ordered pairs and L2 is the Y value. After you've loaded in data into this table, you're going to press your stat key again. Now you're going to arrow over, if you look at the top words, you're going to arrow over to the calc function. And then once you get over there to calc, you're going to scroll down to number 4. Number 4 is a combination of words that mean linear regression. Once you click number 4, now you're going to arrow down again about, I think it's the 5th word down is the word calculate, and you're going to hit that word calculate. Now that's going to come up to a screen that has 4 or 5 lines, one of which is an equation or a couple of values, A and B, for the data that you have just punched in. Now A represents your constant of variation, or it's like your slope, and then B is the y-intercept. And so you'd be able to then plug in the A and the B that they give you and create that linear model or that linear equation of the form y equals ax plus b. All right, we're going to play with this. Everybody needs now to be on page 290, checkpoint number 2. So you can see the data in this table down there, and I was not going to retype or redraw this. So 2003, 277.8, 2004, 301.5, etc., etc. I loaded those into a table. Okay, so I did that stat key, and I went to edit, and I entered those values into that L1, L2 table. Okay, now remember, once you get all, let's see, there's 8 of them. When you have all 8 of them loaded into the L1, L2 table, you're going to hit stat again. Now slide over to calculate. Then go down to number 4. Number 4 is it says lin reg and then in parentheses ax plus b. All right, so that's the one you want. That's our linear regression function. Now when you open that up or click that, it says X list, Y list, frequency list, store, regression equation, and then the very bottom one is calculate. That's the calculate that I was talking about in those steps. Choose it. All right, so if you did all that right, this is what you see. Okay, so there's our linear model. Then underneath it, it says A is equal to 36.852, blah, 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 blah. So roughly a 36.9 or even 37. B, it says, is 161.18, blah, 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 blah. So roughly 161.2. All right, so those are the numerical values that would be in our linear model. So our equation, our linear model itself, is going to be 36.9x plus 161.2. Again, if you don't have a graphing calculator at home, make sure that we go through this together on mine in the classroom. All right, direct variation is something that you guys have worked with in the past. Direct variation means that y varies directly as x. Those models are going to have the form y equals kx. And the reason there is no b at the end, you know, like our typical y equals mx plus b, it's because the y-intercept is always 0. It's always going to pass through the origin in graphed form. So summary of direct variation. In words again, it's y varies directly as x. Another way to state that is y is directly proportional to x. And the model for it is of the form y equals kx for some constant k. So let's take a look at using direct variation a little bit. If you guys turn to page 291, checkpoint number 3 deals with this. Example number 3 obviously in the book does as well, so there's a second example for you to read through and to look through. Checkpoint number 3 says the simple interest on an investment is directly proportional to the amount of the investment. There's your indicator that you have direct variation here. It says an investment of $2,500 will earn $187.50 after a year. Find the mathematical model that gives the interest I after 1 year in terms of the amount invested P. All right, so if we have a direct variation model, remember we're looking for y is equal to k x of some sort. So using variables that fit our situation a little bit better, your interest is equal to rate times your principal. Okay, where r is going to be that constant of variation. It's the rate that's going to change. So now we can take our numbers from our problem. We are asked for the situation where we want to earn $187.50 interest. We don't know what rate's going to achieve that for us, but we do know that we had a principal or an investment of $2,500. Okay, now dividing both sides by 2,500 yields 0.075 for our rate. Okay, so then your linear model is as simply as saying I will equal 0.075 times my principal. There's my model. There's my equation. Direct variation to an nth power can also occur. Areas of circles are one of those kinds of situations. If you remember back to the formula for the area of a circle, area is equal to pi r squared. Okay, r or pi always stays the same no matter what the circle, but r can vary depending upon the side of the shape. So it's always 3.14 times that second power of r. So it's going to be one of those direct variation types of problems. So this is again a sum of that, or a summation of that. Y varies directly as the nth power of x. In other words, y is directly proportional to the nth power of x. And it would just simply, it looks very similar to the other one, but notice that x is raised to a power rather than just being plain. So let's put this to work and see what it looks like. Checkpoint number 4 Now we're on page 292. Again, all these examples that we do, remember, have another one in the textbook that you can look through as well. Um, checkpoint number 4 that we're going to go through at the bottom, it says the distance x an object falls varies directly as the square of the duration time of the fall. An object falls a distance of 144 feet in 3 seconds. How far will it fall in 6? Okay, so on this one, it tells us that distance is some amount times the square of the time or the duration of the fall. Okay, so here's my direct variation model. They give us a little bit of information. They tell us that it falls 144 feet in 3 seconds. So if we plug in that, we can figure out what our constant of variation is. Dividing both sides by 9, I end up with 16 for k. So now I can fit that into my model and use it for an unknown situation. I'd have 16t squared as my equation. I want to know how far it's going to fall if I have 6 seconds. So distance is going to be 16 times 6 squared. Okay, 16 times 36 is 576. Don't forget your label. Direct variation is a case where when the x value increases, the y value does too. When the constant of variation is positive. So as x gets higher, y gets higher. Inverse variation can also occur, and that's going to mean that as x increases, y is going to decrease. Okay, so direct variations look like this. Inverse variations, as x get bigger, y is going to get smaller. So those graphs tend to look like they fall. So y varying inversely as x means that y is inversely proportional to x, and it has a different model. Instead of k times x, it's going to be k divided by x. Moving on to page 293, let's take a look at another checkpoint problem with inverse variation. It says the company in example number 5 has found that the demand for another of its products varies inversely as the price of the product. When the price is $275, the demand is $600. Approximate the demand when the price is $325. Okay, so we know that demand is inversely proportional to price. So demand must be K divided by P. All right, so there's one situation that we know. We know that at 600 units, the price is $275. So use those two to determine what K must be for our price and product model. So to solve this, multiply both sides by 2.75. And we get 1650 is equal to K. So now we can come back and fill that into our model. And we can generalize this for any demand and price thing. So the situation they're asking us to investigate is what happens to the demand if the price is $325. So go ahead and plug that new price in. And if you take 1650 divided by 3.25, you get roughly 507.69, or about 508 units for a demand. Sometimes a problem can have a direct and indirect variation in it. Look at example number 6 in the book. We're going to do checkpoint problem number 6 at the bottom of page 294. So if it varies inversely and directly, you have a combination type of model. So in this particular problem, we're talking about the resistance of copper wire. Let's see, I don't think I typed, yeah, I did type it out. All right, so the resistance of copper wire carrying an electrical current is directly proportional to its length, but inversely proportional to its cross-sectional area. Given that number 28 copper wire with a diameter of 0.0126 has a resistance of 66.17, what length of wire will produce a resistance of 33.5? All right, so first of all, our generic model. Resistance was, okay, it was directly varied to length and inversely varied with that cross-sectional area. Okay, so you can see the K times L, there's your direct variation portion. You can also see the K divided by A, and that was our inverse relationship between our resistance and our cross-sectional area. All right, now, a couple of things in this one that make it a little bit trickier than some. Currently, we have inches and feet going on. Okay, so do you see how they gave you a diameter of 0.0216 inches, but talks about, was it 1,000 feet of resistance? Okay, so first thing we're going to do is we're going to make them match. So 1,000 feet, I'm going to change that to 12,000 inches. Okay, watch so that the measurements in your problems match. All right, so now I can take the information from my problem, I can start plugging stuff in. Resistance, that they give us, 66.17. We don't know K, we're going to figure that though. The length now that we have inches matching inches is this. That cross-sectional area is going to take us a bit of work. Okay, wire is circular, so the cross-sectional area is going to be the area of a circle. So we have 3.14 times the radius squared. Well, now here's another thing. They gave you the diameter. So don't forget to cut that in half. If you cut that in half and then square it, you end up with 0.00004. So that gives us a cross-sectional area of this. Okay? So this number right here is radius squared. So half of 0.0126, that'll give you your radius. Square that amount, you get 0.00004. So pi r squared gives us that number. I can now bring that over here to my area that I need for my model. All right, doing the math behind this one, you get a really little number. -7 power, so 6 little zeros. And then 688 is what my value for K ended up being. Okay, so now in my generic model, I can use K to figure out what the resistance of 33.5 is going to yield me for a length. So 33.5, that's my desired resistance. K we now know, and that's 0.000000688. Length, that's what we're determining. In that cross-sectional area, it's still the same wire, so this stays the same. Okay, so work the math out there. Use your calculator, obviously. We end up with a length of approximately 506 feet. Okay. Joint variation. Z varies jointly as X and Y. That's going to mean it's like a double direct variation within the same problem. So Z is going to be proportional to both X and Y. And you can see it in the model. Okay, so Z equals Kx and also Z equals Ky. You have two direct variations together in one model. Simple interest is something that ends up being joint variation. We know that I is equal to PRT. So you've got your rate, which is the part that changes, that constant of variation, but your principal is what it is and your time is what it is. Your interest is going to fluctuate based on the rate that they give you for it. Okay, so let's take a look at one of these and play with it. Simple interest formulas are pretty simple to work. Look through example number 7 in your book. That one does a simple interest problem for you. The checkpoint actually that I guess I did a checkpoint problem again like usual because the simple interest one was done for you in the book. But it works with the same kind of model. It's still a joint variation model. So 7 in the book does the simple interest one that the previous slide alluded to. I'm going to do a similar kind of one with kinetic energy. All right, so the kinetic energy of an object varies jointly with the object's mass and the square of the object's velocity. An object with a mass of 50 kilograms traveling 16 meters per second has a kinetic energy of 6,400 joules. What's the kinetic energy of an object with mass of 70 traveling at 20? All right, so my model. Energy is okay, so it varies jointly with the object's mass. Obviously, that's the m I chose. And then the square of the object's velocity is where the v squared comes from. So energy equals mkv squared. K still is that constant of variation. Fill in what we know. We know we have 6,400 joules. That first object had a mass of 50. We do not know K, and it had a velocity of 16 meters per second. Okay, so 16 squared times 50 must be 30. No, I got to figure that one out again. 256 times 50. Hang on a sec. Whoops, 16 times 16 times what, 50? There we go, 128. Sorry, didn't have that number written down on my paper for some reason. Now if you divide both sides, we end up with 0.5. So we get 1/2 is equal to K. So now we can come back over here. We're looking for m and v squared if K happens to be equal to 1/2. So the energy for a mass of 70 and velocity of 20 meters per second, we get 400 times 70 times 1/2. And that looks to be 14,000. So our energy for that is 14,000 joules. Okay, I do want you to hand a few in. So take a look at a bunch of them on page 296, but in particular 20, 28, 32, 38, 58, and 64.